Greetings to you. Welcome to Physics with Ben. In today's video, I would like us to look at calculations in velocity time graph. Making use of this textbook, get your calculator and your writing material. Before I start solving this question, I want to say something quickly. I have been through WIAC platform on the internet, that is WIAC e-learning. And as a teacher, what draws my attention on that portal is the weakness of the candidates. WIAC examiners have gone through the result over the years and they have this to say, that candidates perform very poor when it comes to calculations in physics. Candidates struggle with some questions, and one of the recommendations is that candidates should always solve questions from the recommended textbook. And as a physics teacher, I will always recommend Physics New School textbook for you guys over there. And when you carry your Physics New School textbook to study, you see questions that carries a tag like SC/GCE, SSCE. Those questions are potential WIAC questions. I'm not saying they will appear exactly the way they are, but if you take time to go through questions that have this tag, SSCE questions, in your textbook, I believe you will become a potential A1 WIAC candidate. So quickly, I want us to look at something this morning. Let's look at this calculations on velocity time graph. Velocity time graph. Velocity time graph is a graph that depicts the acceleration of a moving object. When we say velocity time graph, it simply means a graph of velocity against time. That is the velocity on the vertical axis and time on the horizontal axis. The slope of such a graph will give you the acceleration of a moving object. We have other ones like distance time graph. The slope of that graph will give you the speed of a moving object. We also have displacement time graph. That graph will give you the velocity of a moving object. We also have another graph for acceleration, which is distance versus time square graph. I did a video on that. Kindly go through Physics with Ben channel and you'll see the video on distance versus time square graph, also known as the graph of what, also known as velocity time graph. I want us to solve a question here quickly. Open to your your New School Physics textbook, page 132 to page 133, exercise 2, question number 25. I have already solved question number 17 of exercise 2, page 132 to page 133. So in today's video, we want to look at question number 25. I read, explain the terms uniform acceleration and average speed. I will not explain this in this video. Just look at this textbook, open to book 2. You see chapter 2. You see this particular page. You will see where they have explained everything. I want to go straight and solve the question 25A. I read, A body at rest is given an initial uniform acceleration. I am solving question number 25A. Yes, question number 25A reads, a body, the page is page 133, New School Physics, exercise 2. A body at rest is given an initial uniform acceleration. Let's say this is our A1, an initial uniform acceleration of 8.0 meters per second square. For time, let's say this is time t1, time for time 30 seconds. After which the acceleration is reduced. And let's consider this as our retardation, known as A2 or minus A2. Let's call it just A2. The acceleration is reduced to what? To 5.0 meters per second square. For the next time, let's say this is our time T2, which is 20 seconds. The body maintains the speed. The body maintains the speed attained for 60 seconds. What I'm saying, there was a constant acceleration and constant speed. When we say acceleration is constant or speed is constant, we mean A is 0 and V is 0. And this happened when time t, that is time 3, was to the period of 60 seconds, after which it is brought to rest. The body finally retards at time t4 is equals to 20 seconds. Full stop. This is the data available from the question. Now the question is, draw the velocity time graph of the motion using the information given above. Now, the first things first we are going to do right now is to draw a velocity time graph. However, we may have something like acceleration time graph, just like we have distance versus t-square graph. It is possible, provided we know how we can go about our equations. But for the sake of clarity, I would like us to convert all this acceleration. We will convert all this acceleration to velocity, because the examiners did not say we should plot an acceleration time graph, but what? A velocity time graph. Do you get it? So let's move on. So we are going to use this equation from V is equals to U plus what? AT. Yes, V is equals to U plus AT. Now, in the first instance, this is it here. In the first instance, we have this. Let us find the velocity for this. So we can say that at this point, our initial velocity was 0. So our equation here is V, let's say V1, let's give it at V1. Our V1 becomes what? Our V1 is equal to what? A1 times T1. Are you with me? Our V1 is what? A1 times T1. That is, this A is a. So our V1 is equal to what? Is equal to 8 times what? Times 30. And what is our final answer? Our answer there should be, that is 8 times 30. That will give us 240. So this is 240 meters per second. So V1 is this. This is the value that we are going to use. Now, we want to look for V2. V2 is given as what? our V2. Our V2 is given as what? U plus AT. Now, in the second part of the motion, our initial velocity is now our final velocity. That is, our U here is equal to what? V1. So in this case, we are saying that V2 is equal to what? V1 plus what? Plus A2 times what? T2. So this is the same thing as what? A2 times what? Times T2. Now, if we substitute, we arrive at this. We have V2 is equal to what? The value for V1 here is 240. 240 plus A2. Our A2 is 5. So we have what? We have 5 times T2. Our T2 is what? 20 times what? 20. If we do that, what do we have? We have 5 times 20. 5 times 20 will give us 100. So 100 plus this will give us 340. So our V2 is 340. Our V2 is what? 340 meters per second. So these are the values that we are going to use on our velocity time graph. V2, V1, V2. That is it. I hope we are cool with this. So to make it more clear, we will rewrite these variables here. So we have just screenshot quickly. I hope you have done that. So our V1, let's start our T1. Our T1 is given as 30 seconds. And then our T2 is given as what? 20 seconds. And then our T3 is given as what? As 60 seconds. And then our T4 is given as what? 20 seconds. Against all this, what is our V1? Our V1, sorry, let me write it this way. Our V1 is given as 240 meters per second. And then our V2 is equal to what? 340 meters per second. So with this information, we are free to plot our velocity time graph now. You don't really need a graph for this particular work, although a graph will also be of help, but you don't really need a graph for this. But let's just use this for the sake of clarity. So we draw a straight line graph, a straight line here, and then another line that will go this way. That is a line. And then we write 0, 0 here. Up here, let me clean this quickly. Up here is velocity in meters per second. And here we write this is time in seconds. So let's go through this again. So a body starts A body at rest is given an initial uniform acceleration. So the acceleration, the acceleration of 8.0 meter per second for 30 seconds is equivalent to this. It's equivalent to this. It's giving an initial uniform acceleration for 30 seconds. So on this axis, the maximum value is 340 and the minimum is what? 240. So we can say that this is 50, this is 50, this is 100, this is 150, this is 200. Okay, this is 50. Let's choose 50. This is 50, 50, 100. Yeah, 50, 100, 50, 100, 150, 200, 250, 300, and 350. Yes, 300 and 350. Let's stop here. We can clean this. We can just clean this to get more space. So this is 100. I'm sorry, this is 50. Sorry, this is 50. This is 100. This is 150. And this is 200. This is 250. This is 300. And this is what? 350. 350 is here. So the time we have the max the time t first time was 30. So we can say that this is 10, this is 20, this is 30. So 30 is here. 10, 20, 30. And then we have time t was 20. So 30 plus 20 will give 50. This is 30 plus 20 will give 50. So this is 30, 40, 50, 30, 40, 50. And so this is 50. This is where time 2 is. So our T1 is here and our T2 is here. So the next one was 60. So 60 plus 50 will give us 110. So let's count. This is 10, 20, 30. Let's do it again. This is 10, 20, 30, 40. I wish to reduce this so that we can have more space on the graph. Sorry about that. That will confuse. This is 10, 20, 30. So this is 30. Then let's add another one. 30 plus 20. That's 50. This is another 10. This is another 10. That's 50. So 10, 20, 30, 40, 50. This is where 50 is. This is your T1 and this is your T2. And then also have another one here. This is 50 plus 60. So this is 10, 20, 30, 40, 50, 60. 10, 20, 30, 40, 50, 60. 10, watch. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. So this is 110. This 110, that is where our T3 is. Our T3 is. Yes, that's where our T3 is. And then 110 plus 20 will give us will give us what? So this is another 10. This is 20. So our graph stops here. So 110 plus 20 will give us 130. So here is 130. And that is where our T4 is. So if you move up here, this is what we have. This is 50, 100, 150, 200, 250. So the first value is 240. 240 is somewhere here. This is where 240 is. This is 240. 240. 240 is here. It's on this line. So 340 is somewhere here. So this is 340. So at this point, we are good to go now. So the question said, so what is here is that on the graph, what we have done is that 1 cm to represent 10 units is what we have done here. 1 cm to represent 10 units. If you want to use WAEC graph sheet, that is what we have done here. On this, we can say that 2 cm represents 50 units. 2 cm represents 50 units. That's what we have done on this axis. So the next thing to do is, let's plot the graph now. Let's give this graph a shape. I have to clean this right now. So I'll be reading and I'll be plotting the graph now. So a body at rest is given an initial uniform acceleration of 80 for 30 seconds, after which the acceleration is reduced to 50. So for 30 seconds, this is it. You trace this point up. You trace this point. This point. Trace it up. The first information, this is where it is. This is it. That's the first information. The second information says, okay, let me read it again. A body at rest is given an initial uniform acceleration of 8.0 meters per second for 30 seconds. That's the first information represented. After which the acceleration is reduced to 5 meters per second for 20 seconds. So the acceleration was reduced to, this is 10, 20 for 20 seconds. This is what you have. Normally, someone would think that this graph is something like this. It's something like this. This is what you see in many physics textbooks. This is not the graph. This is not the graph. It goes up, reduce, come down, then slope. No, this is not the graph. The graph is not like this. And that is why I have chosen this question to solve today. So, the acceleration was reduced. We're supposed to have something like this. But however, we're having something like this for 20 seconds. So you count. This is 10, 20. That happened within 20 seconds. And that will give us the value for the second. This. So you trace this value here up to this point. So this is it. This is what you have. So the graph we have here looks like this. The body starts from rest and moves this way. Do you see that? The body starts from rest and moves for 30 seconds and attains this velocity, 240. The velocity is now reduced to what you see here. It's now reduced is now reduced to this. Yes, that is it. It's now reduced to this. And then let's read again. The body maintains this speed for 60 seconds. It does this. It now maintains a constant speed where you have A is 0 and V is 0. Constant speed for what? For 60 seconds. Let's count. This is 10, 20, 30, 40, 50, 60. This is it. So you put your ruler here again, and dot down, and dot up here. So this body maintains the speed for this. This is it. I see the shape. Now, the second one. The body maintains the speed for 60 seconds. This is where the body maintains the speed for 60 seconds. After which it is brought to rest in 20 seconds. The body was now brought to rest, decelerated in 20 seconds. Now count. This is 10, 20. The body decelerated within 20 seconds. So you put your ruler here, from here to this point. That is where the deceleration took place. So down. That's it. So from here to here there's uniform acceleration. From here to here there's also uniform acceleration. From here to here there's constant velocity, constant acceleration. And then from here down to this place we have what is called what? Deceleration. So you can label it points, maybe point O, A, B, C, then D, E, F, G. Do you see that? Screenshot this diagram quickly.